So first, thanks to all the organizers for organizing this and for having me here. So, what I'm going to be talking about today is actually some of the work that I do, not as a lecturer at Newcastle University, but in my consulting for QCI, for Quantum Computing Inc., which I'll talk a little bit about what they do in general, but mainly the talk will just be on this section of work, which is to try to understand what else might be out there in terms of analog quantum computing, in particular in an optical setting, because that's sort of what we do as a company. Most of the work will be based on this paper, but there will be some other work I discuss. So, first off, why would we want to think about other paradigms? And you might say, well, yeah, there's fantastic work in superconducting circuits and atoms and ions. And I'm not going to deny that's fantastic stuff. I'm not going to do the business person thing and say, oh, yeah, what we're doing is great and what everyone else works on is rubbish, because that would obviously be nonsense. But one fundamental difficulty that there is with a lot of these matter-based systems is connectivity. And it's a serious problem. There are more than one ways to deal with it, including potentially in matter-based systems. If you were at AQC, David Headley presented some of the work we've done in that direction. David's actually here, but he's not presenting this work at INQA. He's there in the audience. I highly encourage you to talk to him about it, but that's not what this talk is about. What we're going to think about here is what can we do in optical systems where light moves around, so you're not limited to a 2 or at best 3D connectivity the way you would usually with superconducting circuits or atoms. I'm not going to be talking about the early analog devices that actually exist in the lab. That's worth thinking about and worth knowing about. And there's a paper we recently got in communications physics that you can see about that, but that's not the topic of this talk. And what we're going to do, because I'm a theorist, is we're going to start off building the theoretical foundations, and then we're going to get into what might you do. If you've been in this game for a while, you probably noticed that my title contained the word towards, which means we don't have the final answer for this yet. Otherwise, I wouldn't have put that word in there. So, as I said before, transverse slicing annealing is a fantastic paradigm. The question here is, are there others? And why do we want to think about this? Well, some physical settings you might not naturally have sort of the kinds of Hamiltonian evolution that you get for where you get adiabatic evolution out of it. And so you might want to think about, can we do computation a different way? Can we do it, for example, using loss rather than this interference between, encoding a Hamiltonian and having a ground and excited state and having interference between different energy levels. So we can set foundations for these abstract questions. What we'll first start off with is the most simplified model, which is just Zeno effects. And the first question we'll ask is, can you get a quantum advantage in the simplest case, which is search? And some of you might be familiar with this. You have these Grover-like problems. It's known that for adiabatic solving, if you use the right kind of nonlinear schedule, you can get the same kind of speed up as you get from a Grover's algorithm. In gate model quantum computing, you basically can search a subspace where you have a Hamiltonian that's either you get one phase if you hit the answer, a different phase if you don't. So completely unstructured, you can solve that in the square root of the number of entries in the number of basically states in the Hilbert space, rather than if you did it classically, you'd fairly obviously have to either guess and check or do something else that would scale as the number, not the square root. So can we have equivalent things based on measurement or the removal of states? And the answer, I'm just going to remove that so it's not in the way of the papers. Sorry. Go back to the slideshow. Maybe I can't remove that. All right. And so this is just some other work that other people have done in this area. And what we've found looking at this is the answer is yes. So this is some work that I did with my colleagues, Jesse Burwald and Rolf Dridi. And what we found is that actually both measuring, so doing repeated measurements of am I in a ground or excited state in this kind of Hamiltonian, or actually having loss, where I say, if I'm not in the ground state, everything just completely gets destroyed. Both of these can actually give you an equivalent quantum speedup. So this is a positive sign that other paradigms might be able to do something useful. And so we can go further and say, well, what if we look at for something that looks more like a realistic problem? Let's say we look at SAT problems. And you have, if you think about this, if I'm using loss as a mechanism and losing one of my two states, I can't just have qubits, because then each qubit becomes a Q, I don't know what you call a qubit with only one piece of one state it's allowed, but that's not going to be able to do valid computation, so you have to expand to your fundamental system being a 3-level system, and then you can say, well, what happens if then I have a 0 state, a 1 state, and an undefined state, and I move from this undefined state into 0, 1 state, and now I have space within a manifold of 3 states to do a measurement or perform loss, and still have a subspace that exists beyond that. And if we look at this, we can say in this setting, a mechanism based on just decoherence or just loss works, but it actually doesn't work very well. And what do I mean by doesn't work very well? Well, I can show on the next slide. So doing something with just loss, what happens, I can look at the adiabatic version. This is nice because here I can actually include a kind of frustration. Basically, I can penalize this undefined state, which you couldn't do if you're just using a mechanism based strictly on loss. So what happens is on these, this is just looking with satisfiability problems. If I look at the spectrum, if I don't do this offset, I get this degeneracy at low angles, so early times in my protocols. This is doing an adiabatic sweep. And this corresponds to the runtime becoming a lot longer. I have an inset, so these are, as I sweep this angle, the success probability, and then these are different total times. And then this is the actual probability versus the runtime in the inset. Notice this is a log scale, so the gray curve's the one that I'm not, that's not shown in the plot. So even though it doesn't look that impressive on a log scale, it actually makes a huge difference. And the reason comes down to the fact that, and in the paper we actually establish what this mathematical structure is. I'm not going to get into it here. But that if you're using only loss, you're not going to have a very effective computation. Even though it will technically work from a theoretical computer science perspective, we generally expect that for NP hard problems, things to, it will still take an exponential amount of time in a quantum setting. So you can show easily that this gives you an exponentially longer time. Strictly speaking, that doesn't actually show you doesn't actually rule out doing this, but it probably indicates it's a bad idea. So now that we've done some of the abstract work, we've shown that we can solve this search problem with different mechanisms. We've done some work to suggest that only having loss, basically having the loss and gain equivalent of an unfrustrated system, probably isn't going to work. Now let's think about optical systems themselves and start thinking about, okay, well, what if we specifically want to do an optical paradigm of processing information and of doing analog optimization? And first, we should probably ask what already exists. And there are 2 paradigms at least that already exist. One is to do variational Gaussian boson sampling. And so this has the advantage that you're fundamentally using the quantum properties of light. You're fundamentally using the bosonic statistics of the light. But the disadvantage is this is variational. It doesn't directly encode the problem. And you'll have issues like barren plateaus, which we heard about a bit in the last talk. The other sort of direction people have looked at this is coherentizing machines. These have the advantage if you really are directly encoding a problem. It's in the name, it's in icing. But using interference. But the role that quantum effects are playing is somewhat unclear. So a natural question is, can we get the best of both worlds? Can we directly encode a truly quantum superposition? And this isn't an easy question, and this is one that we're just starting to look into. But a good way to start here is to outline what some of the challenges are. So the first challenge, which is not necessarily obvious in other settings, is we actually need a true superposition. And there are ways to do sort of squeezing in optical systems, what's called squeezing, I'll talk about this a little more later on, that creates increased uncertainty, but it doesn't really create a true superposition. And one way to see this is that these systems can be simulated classically, at least unless you do number measurements. They can be classically simulated. The open system, there's a technicality on, it's a slightly different criteria that we'll get into a little bit later, but not too much. And then we want a robust way of actually encoding and storing information. There's some indications how to do this already using what is effectively the amplitude of an electromagnetic wave, something called the displacement. And then we need some way to actually encode a problem, because we're interested in directly encoding problems. Again, there's good ideas on how to do this, which is to use interferometry. Basically, you use the fact that the electromagnetic fields will interfere, and you can use that to encode ferromagnetic or antiferromagnetic interactions. One part of this that we're not going to talk about here, or that I'm not going to talk about here, is the fact that unintended photon loss can cause you to lose your coherence. Now, I'm not talking about this because this is initial work toward the direction, not because it isn't an important issue, so it's just worth flagging up as something that we won't discuss here, but it is worth remembering as an important consideration. So for concreteness, let's think of a specific encoding. We're going to do something a little different from the coherentizing encoding. We're instead going to think of something where we have two modes and we've encoded information in which mode has more photons in it. Think, which mode has more light. And you can actually convert this between the phase encoding of the coherentizing machine using these little optical circuits I've drawn here, basically using a beam splitter and using an additional electromagnetic wave. You can go between this encoding of more light in one versus more light in the other, and encoding in which is the phase of an electromagnetic wave. And if we do this, we can again build a little optical circuit that allows us to have a system where we have more loss if one of the two modes coming in is or if both modes coming in have more light than if one has more and one has less. You can imagine if I have this nice encoding where I have two states, I just can take two copies of this and create a ferromagnetic or antiferromagnetic interaction. So theoretically, yeah. So one important issue that I talked about in the beginning is, and this is something that you don't hear about a lot in the coherentizing machine talks, is if I just have the light then leave the system after this, that contains information on what the state of everything is. And that potentially could lead to pretty bad decoherence, even if everything else is fine. So there are theoretical ways that people know to deal with this. Basically, you just mix your light out of phase with a very strong pulse of light, and that overwhelms the signal, and it effectively performs erasure, which is this little box I call quantum erasure here. But it's a consideration you have to think about if you want to really actually do something fully quantum with this. And it's something that you don't find a lot discussed in the literature. So if now we get to one of the, let's say, more complicated issues here, and I'm going to have to go through this a little more quickly, is that we want true superposition. We don't just want this sort of fuzziness and uncertainty. And what this means really is instead of just having the amount of field our light has be a bit uncertain, we instead actually want real separations of I have this and this versus this and this instead of just a continuous sort of fuzziness between them. There's a beautiful quote from Jerry and Knight, one of the key quantum optics textbooks, that says all states of light are quantum mechanical, but some are more quantum mechanical than others. These ones that are less quantum mechanical, you can still have effects like entanglement, but they're easily simulable, although it depends on how you measure them. So there's a table that we have in the appendix of the paper that discusses the situations under which things are simulable or not simulable. Coherent states basically just act like classical electromagnetic waves with a bit of fuzziness to them, but then you can do some other things that this would be quantum mechanical but still simulable. But then when you start including non-Gaussian measurements, you can't simulate it anymore. So how do we actually make one of these kinds of superpositions? Again, this is somewhat known. You can do what's called squeezing, which creates more uncertainty in a certain direction. But that alone doesn't create uncertainty or create the uncertainty you want. You then have to measure, do some beam splitting and measure a photon number. And then if we convert this to the encoding we use, you can actually create something where nicely you have a dip in the photon number difference, and you actually can have exactly zero probability of having exactly the same number of photons in each mode. And you have your peaks away from zero. So you have superposition of this many here, this many here, this many here, this many here. There's a little bit of uncertainty, but you're very unlikely to have very close to the same number. And one of the important things about the interactions I talked about before is this is actually independent of a lot of the uncertainty that goes into this. It's really only dependent in what's called the displacement, which is the overall field strength. And so, if we have these, the question is how good can we make these superpositions given we can't actually predict our photon count? So I realize I'm getting toward the end, so I'm going to speed up even more. And the answer is if you're just looking at creating a superposition of pure electromagnetic waves, this doesn't do a very good job. But if you consider that on some of the interference results we talked about before, this sort of interaction gadget, that actually a lot of the other degrees of freedom in the light, other than what's called the displacement, the overall amplitude of the electromagnetic wave, aren't important. And unfortunately, this isn't showing up correctly, but these ones are. Then what you have is you have very bad infidelity if you consider it overall. But if you say, actually, I'm okay with a superposition of states that have a bit of what's called squeezing, so a bit of extra uncertainty in them, then I can actually get pretty high fidelity with just a superposition of these. And I can say, well, then how many photons have I added from this extra uncertainty? It turns out it's not that much. I can do tricks to adjust these so that I can really have the same amplitude here and here, even in both the modes, even if I measure a different number. Note that I'm only using odd numbers here. I'm only considering the cases where I measured odd numbers. There's a technical reason for that that's in the paper, but I just don't have time to get into it here because I'm already into my questions, I can see. Then the main point here is the ingredients are here for thinking about these paradigms. And the main message I'm going to give for this is just kind of to watch the space. That you can create superpositions. You have the interference effects, which give you a nice handle to actually encode Hamiltonians. There are some points that I didn't have time to get through here. You see, I already was rushing through it, and there are a few other points that are in the paper that I didn't get to here. And this still isn't at the point of actually coming up with a concrete, this is what you build, this is what you do, but we're getting there. And so watch this space for more results. We also have some open system results that I really don't have time to talk to, so I'm just going to skip that one and go to our actual final thoughts, which is that there's some real potential here to overcome the limited connectivity that you have in matter-based systems. But there are also a lot of challenges to overcome. This is an area people should really start thinking about. And in this, I've taken the theorist approach. I've taken an approach of really starting abstractly and getting more concrete. One important point is this represents one strand of work going on that I'm sort of leading. There are many other strands of work going on at the company, including ones that aren't quantum and aren't computing. So don't take this as this is the only thing the company is doing. It isn't. And you can actually get a broader view by looking at the webpage. And now I'll in my talk, and might have time for one question, I guess.
We do indeed have time for one question.
Yeah. A general question. The bosonic sampling is already there, and that only can simulate limited things. Are you thinking something more general?
So I'm thinking of trying to see if there's something you can do where you've actually directly encoded. We've actually directly encoded a problem rather than are doing something that is just sampling from an interesting distribution. Because as far as I'm aware, the bosonic sampling has only really been used variationally in this kind of optimization setting. So what they do is they treat it kind of like, as discussed in the last talk, treat it almost like a black box with some knobs you can turn. And then they say, okay, well, we'll turn the knobs to try to go downhill and find a distribution that has a high probability of finding good solutions to this problem. Now, that's not necessarily a bad approach. What I want to think more about is, can we have something that really you can argue is fully quantum? In this case, the idea of the argument would be to argue that it's really using true quantum superpositions rather than arguing it's quantum from bosonic statistics. Do something that really is truly quantum, but also directly encodes the problem. So the problem's actually directly in how the device works. I can actually have a problem statement that I plug in that's actually part of the part that's processing the light, not as a classical sort of add-on that's then variationally training. Hopefully that's clear. And yeah, this is very much work in progress. This is trying to think toward what we can do in this space, not a final, oh, just go build this.
Right, thank you. Again, let's thank our speaker, and we can have the next one.